quiz you on these. Yep. Really, the only new things we saw today were the rep stos and rep moveFs, right? And I think we covered those plenty fine. So, and the leave instruction. So, moving along, now we're going to see some of the equivalent things in on Linux systems. So, the first thing is that we will be moving from Intel syntax to AT&T syntax. So I already sort of made reference to this when I had to point out that, you know, in Intel syntax, you take the thing on the right and you put it into the thing on the left, right? And so in AT&T syntax, everything's backwards, and it's just there to confuse you. Unless you learned it this way in the first place, in which case Intel syntax is there to confuse you. So, one difference, for instance, this exact same instruction, whereas ESP moved over here to EBP, here it's ESP moves over here to EBP, right? So exact same instruction, just backwards. And you also see that we put these little % signs onto the registers. And here we actually see a $sign on an immediate. So this is one of the, you know, there's only a couple of things that I like about the AT&T syntax. And one of them is that they put the $sign on the immediate to call it out. And that kind of says, look, there's going to be, you know, a hex 14 embedded into your instruction stream right there. Over here, you know, you frequently see just addresses represented, you know, a number could be an address and a number could be an immediate. There's no distinguishment there, right? So, and then again, now this is what makes it a little tricky here, right? This is add ESP plus 14 into ESP, right? And so you have to keep in mind that it's sort of backwards the way it was before, because that doesn't matter so much here, right, with the add, but for your subtract instruction, it definitely matters whether you do 14 minus ESP or if you do ESP minus 14 and then put it into ESP, right? So you have to keep track that even the order of operations, shall we say, is backwards here in this representation, right? So it's not, you know, going from normal left to right that we're used to, right? You don't take the thing on the left and have the thing on the right subtracted from it. You take the thing on the right and have the thing on the left subtracted from it, right? So just keep that in mind, basically. And yeah, I think this slide really needs to be more at the beginning, because this is where I say I use Intel syntax everywhere except now. So whatever. But yeah, so it is important. So part of the reason for this Linux section, part of it's, you know, just to get you exposure to, if you happen, you know, some people are going to be doing it in there, and I just want to, you know, give a little bit of time to doing it in that environment as well. You know, all the Windows people who want to be reverse engineers, you know, this doesn't necessarily matter to you, except for the fact that when you look at talks and things like that, so if you look at security conference talks or, you know, academic research papers and things like that, you have no guarantee in which format things are going to be. So if, you know, someone puts into their research paper a little snippet of assembly code of why this or that is the case, and the assembly code is their proof of something happening or not happening with the compiler, you need to be able to read that just as well, whether it's AT&T syntax or Intel syntax. So getting a little exposure to AT&T syntax is good. But this is the thing that I really hate about AT&T syntax. For those RM32 values, which before we said was a nice base plus index times scale plus displacement, everything's inside the angle brackets. Now for AT&T syntax, you move the displacement outside of regular parentheses, and then you have sort of no notion that it's index times scale, right? And you don't know there's plus signs in between things, right? So it's still base plus index times scale plus displacement. It's just left to you to remember which things are pluses and which things are multiplies and stuff like that. And remember, just like in Intel syntax where each of these things can potentially be optional, right? So I may have, you know, index times 0 plus displacement, and the thing may display it as base plus displacement. Here it could be, you know, just base and displacement over here, or I could have, you know, base plus index times scale with no displacement, so there may be no displacement off here outside of the parentheses. So it may be, you know, just calculate what's inside the parentheses. It may be calculate what's inside the parentheses and then add in what's outside of the parentheses, And that's your address. Now go to memory, right? So that's a bit confusing at times. You actually saw a good example of this in, well, you didn't know you were seeing it, but in Dave's 64-bit stuff, his thing, rather than this, like this right here, this is the nice way that they can say it. Your displacement, they can say, you're displaced by negative E8. Okay, that's good. Or they can say you're displaced by FFFFF something which is negative E8, right? So negative 1 minus, E8, so FFF minus E8, whatever that is. I don't know, 0, 8, 1, 8, something like that. FFFFF 1, 8, something like that. So yeah, this is the nice form, but some disassemblers are not going to give you the nice form. They're going to give you the negative displacement as a negative number with all the F's. Yes?
What is the star there?
What is the star here? This is now just another syntactic thing where it's trying to say, like, well, so this is actually has to do with the call instruction here. So this is sort of one of the more nasty forms that I could give you. We said there were multiple forms of the call instruction. There's relative and absolute. And relative just means like whatever my next instruction is, I want to go some amount relative. When we listed out all those forms, the fourth one was call absolute indirect. And that meant, go through some register, potentially, and go wherever that register is pointing. Well, it's not actually a register. It's an RM32. So you can have up to this most complicated form of an RM32 here. And you're saying, calculate everything in there, go to memory, get what's in memory right there, and treat that like an address, and I'm going to call to that address. So this star here, I believe, is trying to say, like, dereference this RM32, go to memory at that location, and then call whatever's there. But you see, they don't put that for, like, the move one, right? So they don't put the star to say dereference for this other case. It's only, like, with that call instruction. So, yeah, like I said, that's one of the nastier forms that I can give you. But, like the move instruction, for instance, this is what we saw before. And I said I wasn't paying it, I wasn't pointing out this D word pointer. I was just leaving that off most of the time. But that will start to matter on the AT&T syntax because, like I said, it can like call it move or it can call it like move L, right? The L would be to try to say this is move along, and actually I feel like it would be move W in GDB because a word is 32 bits as far as they're concerned. So stuff can get a bit confusing there. Was there a question?
Yeah. So in the AT&T syntax, will move always mean what move do you word?
No, so that it definitely is disassembler dependent essentially. So sometimes it'll be kind of implied like, okay, well I'm using 32-bit registers, for instance. Sometimes they'll add on a little L or something like that to indicate like the length of the thing, but move L is sometimes, like I said, so it can be confusing, and it's kind of, sometimes you have to kind of go based on inference. It's more an issue. It's not so much you have to infer if you're using one program continuously, like GDB, you'll see, here's how GDB represents it, that's fine. But then if you use objdump or something like that, objdump may give a different representation, basically. So they use a different mnemonic. Alrighty, and then, again, just here's sort of a nice form. It's still using like an RM32, for instance, and it's doing the nice EBP negative 8, right, displaced by, or EBX displaced by negative 8. But we can also see that in some tools. I guess I didn't try this in the last class, and I should. I think objdump is the one which puts it in the non-nice form, as we saw by Dave's example code. So I'll show that when we get there. Yeah, so this is what I was saying here where, and it says this, but I think that's different in GDB. So potentially this is where you see this size, you see appending this little size indicator onto the mnemonic for the instruction. So rather than putting like D word pointer in line with the things, if you're doing a move byte, it may do move B, something like that. If you're doing a move long, it may do move L, or if you're doing a move word, it may do move W. But we're going to have to see whether this holds because, like I said, last time I was using GDB, I thought it didn't do this. So, well, no, maybe that has to do with the format specifiers. Yeah, okay. So, yes?
I'm going to regret asking this, but what does it mean when I get a command that actually has a W and an L at attached to it?
I have no idea.
Okay.
The question was, what does it mean when there's a W and an L on an actual
Because I
instruction?
double checked and the one I got yesterday was in fact move SWL.
Move SWL. Interesting. So what it would mean is, in those sort of ambiguous cases, this is why, in some sense, I like the tercity, and there's a better word than tercity, brevity. I like the brevity of this, let's just tack on to say, okay, we're definitely dealing with a byte or 2 bytes or 4 bytes, right? In some sense, I like that, but due to the fact that we have different things using different mnemonics, that's where it gets confusing, and that's when it becomes a detriment rather than a benefit. So what I would do in that sort of case, as we'll talk about towards the end of the class, is I would go back to that behind-the-scene byte and say, like, what byte was this really, and what does Intel say it is? Or I would literally, like, tell my thing, print it for me in Intel syntax right now so I can see what Intel syntax thinks it is. So, yep. All right. So on Linux systems, your go-to compiler is going to be GCC, right? The new C compiler. And this is available, for most NIX systems, as well as OS X, Solaris, and everything else. And it supports many architectures besides x86, so you can, when you're looking at like man for GCC, the problem is then you have a bunch of options for a bunch of other architectures that you're not using, right? So you need to be careful when you're searching for options that you want to pass to GCC. You got to look like, are these x86 options? Are these everybody options? And that sort of thing. But the main option we're going to care about as far as this class is concerned is the -ggdb option. So this is saying output debug symbols onto this binary. So attach debug symbols to this binary, which are appropriate for reading, GDB should be able to read these debug symbols. So there's a lot of different formats you can output debug symbols in, but -ggdb should say, give it something that GDB is going to read. And then, I just say that generally speaking, as opposed to Visual Studio where, you have all that nice little GUI where you select this or that, but I said behind the scenes selecting this or that is still just passing a bunch of command line arguments. In GCC, you just pass a bunch of command line arguments, and typically you wrap that into something like a make file where you set up, whereas in Visual Studio you set all your stuff and then that's your set configuration. In GCC, you'll typically have a make file where that'll specify what options you want to pass, what files you want to put together, in what way, and stuff like that. So the one thing I should say, if you're going to be looking at Linux, etc., so this book is sort of fairly Linux specific. And, AT&T syntax specific. But the reason why I wanted to still have a book for you is so that you could see the alternate descriptions, right? So for all those places where I said, book page 53 and stuff like that, you can go in and you can look at like what it says about, the different jump instructions, what it says about the move instruction or something like that, so that you can get an alternate perspective rather than just going straight to the manual or something like that. And then it has, just additional good information as well. All right, so the basic usage of GCC, as far as we're going to use in this class, well, the basic usage is GCC-O output file name, and that can be on either side of the input file name actually. And so you just do -O for whatever you want the resultant binary to be named, and then input file name would be either, one or many input C files. We're only going to have our very simple examples in this class, so just single input name, single output name, and that's what we're going to do. And then we would also add in the -ggdb. So a final thing that we might do in our Linux VM is GCC-ggdb, means add some debug symbols onto it. Call our output binary example1, right? We typically don't do like .exe and stuff like that on Linux. And then just example1 is my input source file. All right. And so objdump is kind of your go-to disassembler for viewing the entirety of the disassembly of a binary in Linux. So object dump and object file could be potentially even intermediate linking files, like objects that are post-compilation but pre-linking, so you haven't like taken a bunch of stuff and put it together into a final binary. You can still dump those out with objdump, but for as far as we're concerned in this class, the objects which we're going to dump are just binaries that are generated as the output of GCC. And those are, for what it's worth, those are ELF files, the executable and linking format. And we're going to talk about that a bunch in Life of Binaries class. And actually, I should say to the people on the phone, no, that's the intermediate class. Yeah, so for the people who are doing remote as well, you know, I saw a lot of you were not signed up for the Life of Binaries class, but I think you probably do want to be, because the Life of Binaries class, again, is something which is going to help feed into the reverse engineering stuff. So if you're taking this remote and, you know, you thought this was sufficiently useful, I think you'll find the Life of Binaries class as well, so go sign up for that. All right. So one thing about objdump that's useful is this -m Intel thing. So you can override the default AT&T syntax in order to actually see it in Intel syntax so that you can flip back and forth if necessary in order to do it. So Ariel, if you were using objdump to find that thing, try doing like objdump with this thing. What?
I just did,
Yep.
and it switched from move SWL to move SX.
There we go. So I know what that is. That's the sign extend version of move, right? So yeah, so we'll come back to that maybe, but that's really weird that it doesn't do just SX, because that's what Intel says in its manual, move SX, whatever. All right, so -m Intel will override the thing. So for instance, here's a simple example of, you know, my hello world. I do objdump -d hello. I get this init. That's the thing I've been sort of making reference to. That's the function which is called before main potentially. Right, we saw it was named something different for Visual Studio, but there's always this initialization of the C runtime library that goes on before you actually get into main. And so there's init, and then ... Eventually you'll get down. It's basically, it starts at the top, runs all the way to the bottom, just trying to disassemble as much stuff as it possibly can. And so if I flip this to -m Intel, then this is the equivalent stuff, right? So I see here, like, I had end, ESP, and FFFFF0. Back here I had end, you know, this $sign FFFF0 saying that's like an immediate. It's just some constant that's hard-coded in here, right? So maybe I have this LEA ESP +4, and I don't remember that this is an ESP +4. Go to memory. Well, not go to memory. Sorry, it's an LEA, right? So don't go to memory. Just calculate ESP +4, put that address in ECX. And if I want to see it the other way, right, ESP +4 into ECX, right? Back and forth. ECX -4. Well, no, here objdump did the -4, so I don't know what your objdump is doing. Anyways, so that's the back and forth with that. So I'm going to actually show that now. I'm trying to decide how I do this so that I don't just like talk through everything. All right, so you have a Ubuntu VM on your desktop. So you've got VMware Player link on your desktop. Double click on that. And it's going to bring up Ubuntu VM. For everyone who's doing it remote, you know, I sent you the link to download the VM, and you can run this in VMware Player on, you know, Windows or Linux, whatever. So, you know, from within VM Player, you know, we all in the labs will have just this little Ubuntu thing already in our inventory. For people out there, you're going to have to specifically go, you know, file and open virtual machine. But for everyone else, you have Ubuntu, just go ahead and hit play. A virtual machine, or I think it was, well, I don't know what it was. But so now you're going to get a couple of errors because this is set up to like use a virtual floppy drive, but we don't have a floppy drive. So that's fine. It says, do you want to try to connect this device? No, because it's just going to error out again. Right? So no more virtual floppy trying to start every time. Get out of there. I think there might be another error. Maybe, maybe not. What was that?
Takes a while.
Yeah. So this is going to take a while. So I'm going to let that go, and then once we get this up, then we're going to do a quick example of this compilation that I was talking about, as well as the using objdump. So we will we'll go back to doing this, the GCC example 1, and we'll have to go find our example code, which should already be in the VM. And then we'll go forward and we'll do like objdump-d example 1, for instance. So when it comes up, go ahead and use the standard username password that we have for the and I would recommend probably drag it to be relatively large once it comes up. Because you'll want it bigger so that you can see more GDB scroll back and more obj dump output, etc. Ready? Yeah, there we go. So once it comes up, you probably want to expand it to most of the screen. You got your sample code. That just double click on that example zip. It'll open in this little window. Drag that onto your desktop so that we expand the zip file. And then once you've got your expanded code on your desktop, go into Applications. Let's see, where is it? Was it Internet? Nope. Accessories, and then Terminal. And I frequently like drag this to my desktop or something like that so that I don't have to go into the menu ever again. So I'm going to drag that terminal onto my desktop and then open it. So again, Applications, Accessories, Terminal, drag it to your desktop, drag it to your bar up here, whatever you want to do. All right, and then once you get your terminal window up, you're going to do CD desktop and CD intermediate, intro ASM code for class, and then example 1. And for those who don't work in Linux, you can use tab completion. So you just type the beginning of desktop, and then you hit tab. And then you type the beginning of intro, and then you type tab. And you type the beginning of example, and then there's multiple examples. So we just type example 1, and there's no such file. All right, this is the one that doesn't have example 1. So we're going to go to example 2. Man, I'm working on that too much. And so when you're in example 2 and you do ls, you will see your example 2.c, and then you'll see all that other like Visual Studio crud that we don't care about anymore. All we care about is that we have this single example 2.c. We can do like cat example 2.c, and that'll show us the source code that's in it, right? And so recall that that was the one where we did, you know, the 2 times x plus y, and it got turned into an LEA and things like that. Everybody got this up? All right. So now do GCC space dash ggdb space dash O, right? Where we're going to call our output binary example 2, and then just example 2.c. So I'm going to expand that. Right? So gcc-ggdb-o example 2 space example 2.c. All right, that compiles our binary with no fuss, no muss. All right, and so now we can do something like obj dump -d example 2, and then you don't have to, but I would recommend piping it to less so that it doesn't just like spew the entire disassembly all at once. So if I don't pipe it to less, what I get is this. Bam, it like printed it all out and then, you know, plopped me at the end. Or if I pipe it to less, then I get this, and I can scroll using my arrow keys up and down, right? I could scroll anyways before, but whatever. I can now search this as well, right? So again, we see that, you know, this disassembles it. It starts, it has init, and it has all the code for that. Let's see. Where does init call? Well, there's start. Okay, anyways. So there's init, and then there's start, and then eventually if we keep scrolling down, eventually we'll find sub. That was that subroutine that did the 2x times y, or 2 times x plus y, right? And this is interesting here. We see that we we don't have this generating an LEA instruction like we did before, right? Before we had that ECX plus EBX times 2 or whatever it was. This generated completely different assembly. Said I'm going to do some sequence of adds in order to get the same result, right? And then we have main, and we have the call to A to I and stuff like that, the call to sub, etc. And so this is, Intel syntax, and if I want, I can turn the, or sorry, that was AT&T syntax. If I want, I add the dash capital M, Intel, and then fail. Lowercase I on your Intel. Right, so objdump dash capital M space lowercase Intel. And then you get something like this where everything's in nice, clean, aesthetically pleasing Intel syntax. So, it's unnecessary. All right, well, how do I know if I'm doing a mod or something like that? You'll see what I have against percentage signs when we get to the inline assembly, actually. So, all right, so this was just our basic first thing, right? We compiled a binary, and we can dump out the assembly, right? So, objdump is our ghetto disassembler. All right. So, that was that. Do I have lowercase? Yes, I do. All right, so then next we have hexdump and xxd. These are if, for whatever reason, you just want to see like hexdump. I don't know why, but I mean, if you just want to see the bytes, you can see that in objdump. So if you just want to see hexdump in, for instance, the canonical view where you see the ASCII tied to the actual hex bytes, use hexdump dash capital C, dash C for canonical. And if you did that over in your VM, you'd get something like hexdump dash C. Example 2, I'm going to pass that to less again, right? And there I can see that. Well, one thing I see right away is that I have some sort of like ELF signature at the beginning, right? Little ASCII ELF. Or, it could be the Environmental Liberation Front, something like that. Anyways, I can see some strings in here, /lib/ld linux.so, whatever that is. And I see some other strings. So, sometimes for whatever reason you want to look at hexdump. Personally, though, where available, I prefer xxd. So, xxd is my little ghetto disassembler. So, xxd will do a hex dump, just like what we saw, and it'll dump it to file. Well, it'll dump it to standard in unless it'll standard out unless you redirect it to file. So it'll do a hex dump, but the nice thing about xxd is it'll put this thing out to file if you want, and then you can go modify that file and like just change those bytes in the hex dump, and then you can do xxd-r to go the reverse direction in order to take your little text file that you modified and turn it back into a binary file. So I like that. That's, my simple little hex editor. I used this in the past for like hacking like the airport driver for Apple's airport thing to spoof your MAC address. So anyways, xxd, example 2. And then if I just do that, it's just going to dump it out like this. And there's actually some other options, like if I want to put this 1 byte at a time with like spaces between or 4 bytes at a time, but whatever. I do xxd, and then I redirect that to a file, and I say, my dump, something like that. Then I can open my dump with delete text editor nano. Oh no, now the world on the internet knows I use nano. VI and Emacs are for wusses, for stupid people, or something like that. Hate me if you will. I don't care. I don't care what you think. Nano rocks, just like Pine, and it tells you all of its commands right there. Anyways, so like if I wanted, I could, screw this up, and I could change the signature to, I don't know, I think this will be Elf, Wolf, or maybe Ellie. Let's go with Ellie, right? So I hit that to be a 5. So I think 45 is E because we got E, L, F, and that was a 46, and F is 1 greater than E. So I hacked that like that. Go like that, my dump. And I just screwed up like this signature that happens at the beginning, so I'm wondering if objdump will even like open the file later on. But I can do xxd mydump, wait, -r, -lowercase r, mydump. Oh, sorry, is that too low for you guys? Probably. Let's try this. There, no, it's not so low. All right, -r, and I don't even remember what I'm going to do. I think like that. Yep. I'm going to call this, modified example 2. Right, so that -r thing said, take this file in this, format that xxd recognizes, take those hex things and turn them back into binary, which I'm going to actually write out. So now I'm going to try objdump on modified 1. There we go. It says, like, I don't know what that is, but that's not an ELF file. Okay? So I'm not going to read that, and I probably can't even execute it. So let's see. So with example 2, I can do like example 2, and like I said before, I did like 256 as the input. And I do that, and it doesn't tell me what happened. And if I recall correctly, there's something like that. Nope, that's not it. There's like some command you can issue to like echo out whatever the return value was from the previous thing. I can't remember it at the moment. So that's not going to help me. Anyways, let's try something like hello world. All right, so if I execute hello world, right, I got to print out. I'm going to do xxd hello. Hack that. Go in the reverse direction. And then let's see if I can even execute hello mod. Nope, fail. And that's not even an ELF file. Sorry. You hacked it until it wouldn't even execute because it doesn't recognize it as a valid binary file because it doesn't have the right string, the right signature at the beginning. Anyways, that's just saying xxd is your ghetto hex editor. All right, so now talk about GDB. This is our go-to debugger on Linux systems or Mac systems as well. And so as a command line debugger, right, this is not going to be all nice like Visual Studio. It's not going to, have a bunch of windows open for you all at once and things like that. In fact, if you don't tell it to, it won't even like tell you what the registers are right now. It won't tell you where you're currently executing, that sort of thing. So really, GDB gives you nothing unless you ask for it. There are some additional things that there are other debuggers and stuff for Linux that you can use if you want that'll give you nicer user interfaces. But I still decided to go with GDB here because you can pretty much guarantee that anything that has something like GCC for code development on it is going to have GDB on it as well. And it's frequently on systems by default. So the syntax for starting a program in GDB is GDB and then just the program which you want to start. But in order to make this useful for us, we're going to talk about using a commands file. So we're going to give a -x and then a file name. And that file is just basically going to have a list of GDB commands, just the same kind of thing you would type in when you first get into GDB. Things like display this register, display that register, set a breakpoint, things like that. So we're going to put those sort of things into a file, and then we're always going to run GDB with this commands file so that it'll always print out whatever we want to see. All right, so yeah, that's just -x, gives a commands file. And this is absolutely essential to using GDB if you're going to use it for any amount of time, which you will be at the end of the day when you're doing your little example thing. you want to be using -X, which has all the commands you want to do. And so it looks like I didn't move the commands thing. I want to move that now. I think, there we go. This is what we're going to use as our initial commands file. So go ahead and start, either if you grab the slides, copy this into something, but in your Linux VM, you're going to want to have this sequence of commands in some file called whatever you want to call it, but I'm going to call it like command. Nano command, whoop, paste that in there, and then I have that in my commands file, and I can do, in Nano, I can do Control O and out, etc. Use whatever you want. But I'll come back to this in a second to let you type it out. Or skip ahead in your slides. It'll be in your paper slides and write it out. But I need to move this because I want this to be after that. All right. Yeah, so I recommend, you copy and paste that thing. If you don't have a preferred text editor, and if you are just using Nano, you can copy and paste by doing like Control K and something else. Yep, Control K and Control U. Yep. You can just go to a line, hit Control K, and then hit Control U a bunch of times, and you'll get that same line output again. And then just go through and modify the registers. So for instance, one thing we can see from this is in GDB, registers are going to be prefixed with the $sign now. So GDB's writing things has nothing to do with AT&T syntax. It's just GDB syntax. All right, does everyone pretty much have it up? Almost? No, I still hear typing. And actually, I'm going to say, change this 32XW, get rid of that, that's like too much. Let's change that to like 16. All right, so I've got my file in a file just called cmd command. All right, so now I'm going to go back to that example 2 like everyone else should be in right now. All right, so you should be in example 2. You should have your copy of your command file, let's say in the exact same directory, which I don't right now. So you can, for instance, execute GDB on example 2 by doing GDB -X, your command file, and then example 2. And press return. And that's going to start up GDB. And it's going to set a breakpoint because the very last thing you had in your command file was break main. So it's going to say, set a breakpoint at main. That's what we see right here. And then, we can run the program, look at the program. But the main thing I'm going to say for right now is do run. We haven't learned this instruction yet, right? We're going to go through and learn all the commands for GDB, but if you hit run, then you will see this sort of output where you get to see some disassembly, you get to see the registers, you get to see 16 D words worth of the stack, and things like that. So that's all I'm saying we're going for with this command file. We want it so that every time we step one instruction at a time, this sort of output is going to be displayed. So I'm going to exit out of there. All right. We'll go back to here. So now we're going to learn about our commands within GDB. So once you're actually inside GDB, the most important command is help. Okay? So you can use help from within there. So if you want, you can do this. You can watch the slides up there and, stay in GDB down here if you want. So you can do something like help, and then that'll tell you all the different types of help you can get. And then you can just keep doing help and drilling down on something. So for instance, I can do help on breakpoints. So help breakpoints. Now it'll list all the different types of breakpoints all the commands that pertain to breakpoints. So there's awatch, which is set a watch point for an expression, blah, blah, blah. Got a bunch of those different things. And for each of those, I can then also drill down and say, say help trace. Right? And eventually it'll say, okay, well, trace has a certain form, trace and then a location, and a location may be a line number, et cetera, et cetera, et cetera, right? So this is kind of like a terminal leaf in the help tree, right? Eventually you get to something which says this is the syntax for this command, and, there's no other list of commands, basically. Right, so help is the most important thing. When in doubt, type help, and then just be like, I don't know, I guess I want to look at the stack or something like that, and then help stack, and then see if anything looks like it, sounds like what you want to look at, etc. And so you just keep drilling down. All right, so then the next command, now that we have like this command file full of stuff that you don't necessarily understand yet, like we saw, run is the next command you might want to know so that you can just start the executable and it'll do whatever those sequence of instructions are. So there's typically like a long form for everything and there's a short form, like you can just type R and that's the equivalent, but I will try to use the long form for everything, and if you do these long enough, eventually you just do the short form, right? So then just as an important note, if you want to pass command line arguments to a program, right? So we have example 2, and we want to run it with some input. If we don't run it with some input, it's going to crash. Then what you would do is, run and then your argument vector as normal. So as if you were running it from the command line, you would do run and then whatever arguments you want. So you could, example 2, you could do run 1 or run 256 or something like that from within GDB. I think you can also specify them just on the command line outside, but I'm not sure. I'm going to go check quick. But there's not a good way to check that unless I set breakpoints and stuff to see that those registers are getting set. So never mind. All right. Another thing that I found out about recently, which is kind of silly, is start. And start is the equivalent of break main plus run, right? So I had you put a break main inside of your end of your command file. You could just put start there, and then it would do break main plus run. But I kept them separate for now because in some cases, like example 2, right, we want to pass some command line things to run. So we just have a separate break main, and then I want you to do the run manually. And then you can pass command lines or not pass command line arguments, etc. All right. So, if I were, so you can use help display to see like the full description, but you saw display was the bulk of those commands that I had you put in the command file, right? So display prints out a statement every time the debugger stops. So if you hit a breakpoint, it's going to print it out. And then if you do like a step over or step into instruction, you're just executing one instruction and then you're stopping. And so a display will say print out this information each time. And so you saw I had like display EAX, display EBX, display ECX, right? So all of that is just so that each time you step over an instruction, it'll print out all all of the registers. It'll print out that stack. Display with the special format specifier says display instructions, right? So I had a display /I EIP that says display some number of instructions at EIP. So the format for display is display and then a slash sign, and then some format specifier, where we'll talk about the format specifier here, and then expression. And I need to add a slide for expression, but I haven't done that yet. So anyways, format can be one of the following, or some combination thereof. Format could be I, which would say display whatever this expression is, whatever is at memory at this expression, display that as a sequence of assembly instructions. So I don't care if they really are assembly instructions or not. Just treat them like assembly instructions and interpret them per, the bytes which specify, a push EBP or whatever. So if I see 55, that's a push EBP or whatever it is. And then just, if you see 55 GDB, print out whatever assembly instruction would correspond to that. But so typically you use this just on display /I EIP, and then that'll just display a single assembly instruction. Or the format specifier can use a number, so like 10I, and that'll say display 10 assembly instructions. And I didn't fix that either. I should say, Does that description sort of make sense? Other than the fact that you don't necessarily know whether you need angle brackets or not, right? That's ambiguous, but does that make sense that part of the format, well, and it's not just one of the following, it can be a combination of the following. Right, so you can have some combo of potentially like X to say, I want to display something as hex, and then I want B to say I want to display a byte as hex, or I want to display, a half word as hex. So this is where the ambiguity comes in. The format specifiers in GDB do not necessarily match, well, they definitely don't match the Intel sizes. So when GDB says use W for word, GDB means 4 bytes, and potentially it probably means 64, or potentially means like 8 bytes or 64 bits in the 64-bit one. I've never tried that, but probably, I'm not sure. So this is kind of one of those things where in order to figure out, like what corresponds to what, you're going to have to like look at the manual probably a bit in order, well, either look at this or look at the manual to say, okay, well, how do I display something as a byte? How do I display something as 2 bytes, etc. But these are the things. So you can do B, H, or W for byte, 2 bytes, or 4 bytes. And then X or D for like if you want to display as hexadecimal or decimal. And then S is a very useful one. This says go to memory wherever this expression is and treat this like a string. So what that means is it means basically print each of these bytes as an ASCII, whatever the ASCII version of that would be, and then only stop when you hit a terminator, a null terminator, right? Because that's a string. It's some sequence of ASCII bytes followed by a null sign. And so it's just going to keep trying to interpret these things and trying to print them out until it finally hits a null character. So if you happen to be not looking at a string, it could just print out a bunch of junk and garbage, right? But if you print out a string, it's great, it's nice, all of a sudden, yeah, bam, that memory address is a string. I know it, right? And then you have number. So number, you could actually print out like 2 strings. So if you think there's an array of strings, like that argv, you could potentially do 2 strings, and it'll say, okay, I'm going to go to memory, I'm going to like read all of that, and that's going to be, 1 string, and then it's going to go to the next byte after the null terminator, and then read all that and treat that like the second string. So using this number, you can like display 2 hex bytes, or 2, decimal words, or 2 strings, or 10 instructions, things like that. So between the format and the expression, that's how you specify what you want to display every time the debugger stops. And you can use info display to see like what do you currently have set for display. So if I did this, so if I did this command again, and I start out, and I haven't even executed, I haven't started the thing yet, but if I do info display, it's telling me, okay, well, display 1, you asked for, 10 binary instructions at EIP, right? We didn't actually put the B, but it's saying that's what it's actually using. So saying, and this Y is like, is it enabled or not? So this is enabled, that's enabled, they're all enabled. So it says your first display was 10 binary instructions. Your second display was, a /X for EAX, right? And the second one was /X for that. Ninth one was 16 words, right? So words in GDB are 4-byte values in hexadecimal starting at ESP, right? So 16 D words, as we call them, or words as GDB calls it, starting there. So info display like that, and like I can do undisplay, say 9 or something like that, and then that deleted that, right? So if I don't want to see anything anymore, if I think that's not useful to me, undisplay deletes it. That's all I want to say about display. All right. Another extremely useful command, and you're going to use this a lot, is X for examine memory. So it's like display in that it takes a format and it takes an expression, where that expression is typically, so the big thing about X is whatever your expression is, it's going to treat that like a memory address, and it's going to go to that address, and it's going to display whatever's at that address, basically. So X is something where it's always dereferencing this memory address and going to memory and displaying whatever is currently there. So always examines the actual memory given by an address in your expression. And you can, again, just use the format specifiers to say, I want to examine memory as an instruction stream, as a string, etc. And so there's X, which dereferences this expression and goes to memory there. And then there's print, which doesn't dereference it. It just kind of, so if X is move, right, it goes to memory. Print is LEA, it doesn't go to memory. So it just says, if you can maybe give some calculation, like your expression may be like EBX plus EAX or something like that. So print /X, maybe. EBX plus EAX, and then it'll just calculate, add those together, and print out whatever the result value is. So we have a couple examples right here. So this is where, again, this syntax can be a little confusing, but on the right-hand side of that slash, right, that's all format specifier, right? So the X over here means examine memory. The X to the left means examine memory. The X to the right means display it as hexadecimal, right? Because per the previous thing, said you can have a hex format specifier, X, or a D format specifier, D, right? So examine memory as hex at EBP. So it's going to take EBP, whatever's in that register, it's going to say, I want to treat that like a memory address, go to that memory address, and examine what's that memory there. And so what happened here is EBP happened to contain BFF, BC, B78. So that's what was in EBP, but X says examine the memory at that address. And so then it says in memory at that address is BFF, BC, BE8. Right? And that's probably a saved frame pointer from the previous thing, right? Because those EBPs are always pointing at the previous frame pointer, right? That's that linked list. That's why they kind of look like they're the same, both stack addresses, roughly in the same range, etc. Right? But if I did print /X rather than X/X, it's not going to go to memory. It's just going to say, okay, well, EBP is BFF, BC, B78. And then alternatively, let's pretend that I had the number 1 in EAX, right? And I did X/X EAX. It's going to try to go out and examine memory at the memory address 1. Well, for this current process, the memory address 1 is not valid. Nothing's stored there. So X is just going to say, sorry, can't go to memory at that address. That's not, there's nothing there. But print is fine with it. Print just says, I'm going to print out the 1, which is in this register. So, think of it either way. I think of them like move versus LEA. One of them goes to memory, one of them doesn't. But Do whatever works for you. All right, so then we have a variety of commands to actually set breakpoints. And actually, hold on, I'll see how many I have more before you can get you to lunch. All right. So then we have a bunch of commands for breakpoints. So obviously, just like in Visual Studio, you potentially, Visual Studio, you had a GUI click where you said, I want to break right here. In GDB, you use break or the B command. And the big thing here is, if you have debugging symbols, right, everything we're going to have has debugging symbols. You can issue things which have symbol as sort of the destination where you want to break. So you can do break main just like you have in your command file right now, right? But let's say you're trying to reverse engineer something on Linux, like we're going to be doing with our example at the end of the day. You won't necessarily, well, I guess our example at the end of the day does have symbols, but you won't necessarily have symbols for the thing, and therefore you can't just do break main. So potentially you have to give a hard-coded address, and you want to say, I want to stop at this address exactly. In that case, the syntax here, and probably should put a space here so that everything's on the same line. Right, so with symbols, the syntax can be just break on some symbol, whatever address, break sub, break main, break memcopy, something like that. If you want to give a specific address, it's B and then star and that address. So you have to put the star before, otherwise it'll get confused and it won't set the right breakpoint on the right address. And one other miscellaneous note here. GDB's interpretation of where a function begins, if you have symbols enabled and you say break main, it assumes you really want to break when main starts doing something. And so all of that compiler-generated, push EBP, move ESP to EBP, whatever, all of that gets skipped over. So when you do break main, it actually says, okay, after you've done all that, after you've pushed your callee save registers, after you've allocated your local variables, I'm going to set the breakpoint on that instruction rather than the very first instruction. So I'll show how we can actually see that in this thing. Wow, that's a fast timeout. Right, so I'm going to execute this again with gdb-x, your command file, and example 2. You do that, it did break main, right? That's why it says breakpoint 1 at, whatever address. That happens to be the address of main. Right, line 8, it's talking about C source code, line 8. And now if I do that run again, I've made my window sufficiently big in big text that I can't see all of my instructions at once. But what it's saying here is the first instruction of main, as far as it's concerned, is this move, EBP plus C into EAX. But you can see right there that this is actually main plus 9. So we're actually 9 bytes into main at this point, at the very first point we break. So if I wanted to see what the very beginning of main looked like, for instance, I would have to then go back in and do something like x/i say 10i at main, something like that. So here, this is, not going to be skipping over anything. This is just literally going to be replacing main with a specific address. And so if I do this command, and again, did I move this down again? If I do x/10i main and press return, okay, now this time it'll actually disassemble starting literally at the first address in main. And we can see that the breakpoint got set here at main plus 9. So GDB decided, well, the programmer doesn't really care about those first automatic compiler-generated instructions. They care about the stuff they wrote, right? So all of that got skipped, right? We have some push EBP, the move ESP to EBP. We haven't seen this sort of construction before, this ANDing ESP with FFFF0. So I'll just say about that it's like, what is this trying to do, right? If the least significant 4 bits are all 0, and we know that any time we AND anything with 0, it's going to just be 0, then, well, I'm not going to do it on the board. It's basically going to say whatever the last 4 bits are, the last nibble of whatever ESP is right now, it's going to be turned into 0. So potentially ESP might get subtracted. Let's say ESP is, you know, BFF 00004, something like that. After this AND instruction, that 4 is going to get wiped out as the last nibble. And so ESP is actually getting moved down a little bit. And what it's getting moved down to is a 16-byte aligned address. And this, again, is just one of those miscellaneous, you know, chalk it up to optimization things. If you go search through the Intel thing, it may say something about, like, it's better if, you know, stack copies start on a 16-byte aligned address or something like that. So this is just GCC decided, hey, we're going to try to follow some optimization guidelines, and we're going to try to, you know, align our stack for a 16-byte address, something like that. So anyways, we haven't seen that before, but then we get back to something, something we've seen before. Subtract hex 20 from ESP because we're going to allocate space for local variables, right? And actually, this is more than enough space for local variables for reasons that we'll talk about later after we get back from lunch. So let's you go here, back at 1. Any questions on the phone before we leave for lunch?